In this video, I'm going to go through Cambridge International A-Level. This is going to be the paper 1, the multiple choice paper, and it's the one from 2019. Okay. Right, the first question is about the Boltzmann distribution, then, which I've drawn on the right-hand side. The temperature of a sample of an inert gas, okay, is increased. So we've got the black line there, but number of molecules on the y, and energy on the x-axis. This is the black line. This is the low temperature, and the red one is the high temperature. Okay, right. So which two columns are correct? So if you increase the temperature, the number of molecules with the most probable energy, okay, and the most probable energy at the height is there. And as you can see, that peak is lower than the most probable energy, yeah, at the lower temperature. So we want either A or B here. The number of molecules with high energy, obviously at higher temperature, that's going to increase. So our answer is B. Okay. Right. Okay, so this is about calculating the relative atomic mass from mass spectrometry. Here's the mass spectrum shown, relative atomic mass. So what you have to do is this little thing here. Okay, so what we said, if you've got 100 atoms on average, 3 of them are going to weigh 112, so 3 times 112. 56 of them are going to weigh 114, 41. So work that little sum out, and you get the answer there. That's equal to 114.35. So and round that up to 114.4. D is our answer there. Okay, this is a bit of a long question. A washing powder contains sodium hydrogen carbonate as one of its ingredients. In a titration, a solution containing 1 gram of the washing powder requires 7.1 centimeters cubed of sulfuric acid for complete reaction. The sodium hydrogen carbonate is the only ingredient that reacts with the acid. What's the percentage by mass of the sodium hydrogen carbonate in the washing powder? Well, we need the equation for the reaction between sodium hydrogen carbonate and sulfuric acid, and you can see there, importantly, it is a 2-to-1 ratio, 2 moles of sodium hydrogen carbonate to 1 of sulfuric acid. So what we're going to do now is work out our moles of sulfuric acid. So moles H2SO4 is going to be equal to the concentration multiplied by the volume, dm cubed. Our concentration of sulfuric is 0.1. The volume, 17.7.15 centimeters cubed, so that's over 1,000. That works out to be 7.15 times 10 to the minus 4 moles. And as we said earlier, it is a 2-to-1 ratio of sodium hydrogen carbonate to sulfuric acid. So moles hydrogen carbonate, we've got to double that times 2, which gives us 1.43 times 10 to the minus 3. Okay, now we need to work out our mass of sodium hydrogen carbonate. So mass is equal to moles times the MR. The MR of sodium hydrogen carbonate is 84. So that's going to be 1.43 times 10 to the minus 3 multiplied by 84, which gives us 0.12. So we need to work out the percentage by mass. Well, we've actually got 0.12 grams of sodium hydrogen carbonate in 1 gram of the washing powder. So the percentage is going to be 0.12 over 1 times 100, 12%. So C is our answer there. Okay, now on to electronic structure. Right, the outermost electron in an atom of neon occupies a particular orbital. Well, here is the electronic structure of neon. 1s2, 2s2, 2p6. Which row shows the relative energy and shape of this orbital? Right, it is the outermost electron. So we're talking about the electron is in the 2p orbital. Okay. Right, compared to the energy of the 2p, it was the highest one. Okay, so it's going to be higher or equal. So it's got to be A or B. So these two are wrong. And what is the shape of the p orbital? Well, obviously it's that one there. So the answer is A. Okay, in which species is there a lone pair of electrons? Right, so most of those species are pretty, apart from methane, they're pretty kind of obscure. Let's draw a dot cross diagram well, we know methane has got 4 bonding pairs. If I just draw dot cross diagram for that. So carbon, of course, group 4. So we've got 4 dots from the carbon there, so there's no lone pairs, 8 electrons in their outer shell, so it's not that one. Right, let's say it's CH3 minus. Okay, now we can turn that into CH3. We're going to get rid of one of those hydrogens, but it's going to leave its electron behind. Okay, that X there's come from the hydrogen. So this would be CH3 minus. And you can see that does have a lone pair of electrons. So this is the answer C, just to show you that it couldn't be B. Well, if it was B, you'd be missing those 2 electrons. So B would just be like that. CH3 plus would be like that. CH3, well, that would actually be a free radical. Have an unpaired electron there. So C is the answer there. Okay, we've got an ideal gas equation calculation here now. An evacuated tube of 400 centimeters is filled with gas at 300 K and 100 kilopascals, and the mass increases by that. Right, so let's use the ideal gas equation. PV is equal to nRT. Well, we're going to work out the number of moles we've got in that. Okay, so N is going to be equal to PV over RT. Once we've worked out the number of moles from that, then we can work, because we know that mass is equal to the moles divided by the AR of the gas. Rearrange that. AR is going to be equal to moles over mass. So we can work out the AR, the relative atomic mass of the gas, and then decide which one, argon, helium, krypton, or whatever. So let's do the calculation for N. Now you have to be careful here with the ideal gas to use the correct units. Right, P, the pressure has got to be in pascals, not kilopascals. So we need to, that's 101 times 10 to the 3 pascals. Volume, really tricky. You've got to make sure that's in meters cubed. So we've got not centimeters cubed. So we've got to divide by 1,000,000. There are 1,000,000 centimeters cubed in a meter cubed. So we're going to have 400 over 10 to the 6. R, the ideal gas constant, 8.31 from the data book. And T, temperature in Kelvin, is 300. So we work that out there. We get the number of moles to be 0.0162. That comes to. Now we're going to work out the AR. So AR is equal to the moles. Sorry, I got that one the wrong way around. AR is mass over moles. Very bad. So AR is going to be equal to the mass of the gas, they tell us, was 0.65. And the number of moles is, we just worked that out, 0.0162. That comes to about 40, which is the AR of argon. So A is the answer there. Okay, number 7, under which conditions will nitrogen behave most like an ideal gas? Well, it's important to realize for an ideal gas, we're assuming no attraction between the molecules, which is not true if they get close to each other, because you're going to get London forces or Van der Waals forces. between the molecules. So you don't want the molecules too close together. So that means you don't want high pressure, you want low pressure. So it's got to be B or C. Also, we assume that the volume of the molecule is essentially 0 compared to the volume of the container. That's another assumption. Now, which one is it? So it's we want low pressure, but we want high temperature, because then those molecules are flying around really quickly and don't have a chance to attract each other, and they take up more volume. So they're further away, so they don't attract each other. So B is the answer there. Low pressure and high temperature. If you like, when gases start to liquefy, then they stop behaving like gases, because then the molecules are going to attract each other. So what you do to liquefy a gas, you want high pressure and low temperature. So yeah. Okay, 2 reactions and their enthalpy changes are shown here. Okay, these data can be used to calculate the enthalpy change of the reaction shown. Now, they're being a bit mean here, because if you look at this one here, well, what is this one here? This is delta H of formation for C2H2 ethine. And if you look at this one here, this is also delta H of formation, this time of ethene, C2H4. And this one in yellow, right, this is just a reaction. Okay, now if you wanted to find out delta H for a reaction and you're given delta HF values, which Hess's law cycle would you construct? So we wanted to work out this for this yellow arrow, which we know what it is in this case, it's -175.8. And we're given delta HF values. What is the third thing we put in our Hess's law cycle? Well, we put elements in their standard states down here. Okay, in this case we have got the elements that are carbon, and we've got hydrogen. And if we were given delta HF values, well, we're going to put the arrows up. That green arrow, we're forming 1 mole of C2H2 ethine. That red arrow, we're forming 1 mole of C2H4. Okay, so let's put the numbers in there. Now look, we are given on the red arrow here, this is the enthalpy of formation of C2H4. Yeah, that's plus 52.2. This green arrow, well, this is what we're trying to find out here, delta HF of C2H2, and that's called X, so we'll call that X. Now we can see here from our Hess's law cycle, if I want to do that green arrow, X, it's equal to, well, what have I got to do? Well, I've got to go along the red arrow, I'm in the direction of the red arrow, so I keep the sign, so that's plus 52.2. And then I've got to go along this yellow arrow, but going against the sign, so going against the arrow, so I change the sign there, plus 175.8. And we work that out, and it gives us 200 plus 228 kilojoules per mole. So that is our answer, is D. So essentially you're using, it's the Hess's law cycle where you use delta HF values. That's what you need to use there, but they say they've been a bit mean by not saying that's delta HF, and you've got to realize that. Okay. Okay, ethane dioic acid can be oxidized by potassium permanganate, dilute sulfuric acid. The products of the reaction are carbon dioxide, water, potassium sulfate, and manganese sulfate. Do we need to, right? So in this equation, each ethane dioic acid loses 2 electrons and it's oxidized, shown by this equation here. We need to, before we can answer this, we need to write down the equation for the manganate in the other half of the equation. So manganate, it tells us, gets reduced to the Mn2 plus ion, manganese 2 sulfate. We need to put in, so we need to balance that half equation for oxygen. So I need to put 4 waters there. I need to balance for hydrogens now with H pluses. Well, I've got 8 on that side, so I need to put 8H plus. Now I need to balance for charges. I have got a total of 7 plus on this side of the equation and only 2 plus on this side. So I need to put 5 electrons in here. Okay, so 5E minus there. Okay, so now we've got that half equation. We can see if we wanted this when this reaction occurs, and we don't worry about the sulfate ions, the spectator ions, we've got to multiply, because this is 2 electrons, we've got to times this by 5 and multiply this one by 2. Okay, so how many water molecules are produced when 5 moles of ethane dioic acid are oxidized? Okay, well, 5 moles of ethane dioic acid. So if you multiply this by 5, you can, well, let's see, we can see the ratio of ethane dioate to the manganate. That is 5 to 2. Okay. So if we are oxidizing 5 moles of ethane dioate, that means we must have reduced, if you like, 2 moles of manganate. It's asking us how many water molecules are produced. Well, we can see for every 1 manganate, we produce 4 water molecules, but we're doing 2 of them. So that means our answer is going to be 8 molecules of water, 8 moles of water. So the answer there is B. And you need to know that half equation between manganate, the half equation of manganate being reduced to Mn2 plus to be able to do that question. And you should know that half equation anyway, really. Right. Number 10, okay. Hydrogen iodide gas decomposes reversibly to produce iodine and hydrogen. The position of equilibrium for this reaction may be altered by changing the external conditions. Which row correctly describes the change in the position of equilibrium? Okay, right. If we increase the pressure, well, let's have a look at the pressure. We've got 2 moles on the left-hand side and 1 plus 1 there. We've got 2 moles on the right-hand side. So pressure has no effect. So it's got to be C or D. Now, effect of increasing the temperature, look, this is endothermic, positive. Le Chatelier tells us if you increase the temperature, it's going to try and decrease it by moving the endo direction. So it will move to the right. Increase the temperature, it will move to the right. So the correct answer there is C. And more on equilibria. Okay, the reaction between sulfur dioxide and oxygen. Here we got that there, and they give us the value for Kc. In the equilibrium mixture, the sulfur trioxide they give us that, okay, and the sulfur dioxide concentration. Well, we've got to write down the expression for Kc first of all. So the expression for Kc is going to be concentration of SO3 squared divided by the concentration of SO2 squared multiplied by the concentration of oxygen. Okay. Now, what do we know here? Well, it tells us, we know the value of Kc, yeah? We know the value of sulfur trioxide, but it tells us sulfur dioxide concentration is twice that of oxygen. So let's let the oxygen concentration equal, let's say that is X, okay? So that means then that the SO2 concentration must be equal to 2X. We're going to put all those numbers into the equation. The only thing we don't know is X, so we can find that out. So let's do that. So we get, let's put the numbers in. Kc is 280. So we get 280. SO3 concentration, they tell us, is 6. So that's 6 squared. Divided by the concentration of SO2. So that's 2X all squared. And the concentration of oxygen is X. Let's simplify that. We get 280 is equal to 36. Now 2x squared, don't forget that's going to be 4x squared, 4 because you square the 2, 4x squared times x So we've got, carry on doing that. I'll go up here. So you get 280 is equal to 36 over 4x cubed. 4x cubed then rearrange is 36 over 280. That gives us x cubed is equal to 36 over 280 divided by 4. All right, just evaluate x there now. I'm running out of space a bit, so I'll go over to the left here. So x, just evaluate x from x cubed there is equal to 0.318. Now, axis, we need the sulfur dioxide concentration. That's the concentration of oxygen. So that's sulfur dioxide is 2x. So SO2 concentration multiply 0.318 times 2 gives us 0.636. So D is our answer there. All right. Now, 1.15 gram of a metallic element needs 300 centimeters cubed of oxygen. Okay, so we can work out the moles of oxygen. Yeah, to form an oxide which contains O2 minus ions. So let's work out the identity of this metallic element. Now we have to bear in mind, look, we've got calcium, magnesium, they're group 2. So the formula of those oxides is going to be XO because they form 2 plus ions. Potassium and sodium, they are going to, because they're group 1, they're going to form an oxide of the formula Y2O, where Y is the metal. Okay. Now, let's work out our moles of oxygen first of all. So that's going to be the volume of the gas divided by the volume of 1 mole, 24,000 centimeters cubed. That gives us 0.0125. Okay, now let's do for calcium and magnesium for X. Okay, so for XO, the moles of X has got to be equal to, well, that's for O2, isn't it? So moles of X is going to be, it's going to be double the moles of O2. So that's going to be 2 times 0.0125, which is equal to 0.25. Okay, so now we know the moles of the metal. Well, we've got to see, does it fit in with that? Okay, now we know that moles is equal to mass over AR. So let's work out the AR from that. So AR is going to be equal to mass over moles. The mass, it tells us, is 1.15 grams. Divided by the moles, 0.025. That gives us 46. Now, we've got calcium. The MR of the atomic mass of calcium is 40 and magnesium is 24. So 46 doesn't fit in at all. So it can't be either of those. It's definitely not that. Okay, so we've got potassium or sodium. Let's work out what it is there. Now, these form the formula, the oxide formula is Y2O here. So the moles of Y is going to be to the moles of oxygen, O2, divided by 4. Because you've got 2 Ys for each oxygen atom, so you've got 4 for each oxygen O2. Okay, so that's equal to, sorry, multiplied by 4, beg your pardon. Okay, so the moles of Y is going to be equal to 0.0125 times 4, which is equal to 0.05. Okay, so let's do that. We work out the AR like we did before. So the AR is going to be moles, sorry, mass over moles. The mass is 1.15. The moles is 0.05. that's equal to 23. You should probably recognize is the AR of sodium. So D is the answer there. Okay, so that one requires you to be able to do mole calculations and realize that the difference in formula between group 1 and group 2 metals. Right, 13, relative melting points of 4 consecutive elements in the periodic table. This is about periodicity then, okay? And they all have proton number less than 20. Okay, which element is in group 16? Well, group 16 is this one here. This group 6, on there, 16, yeah. Right. Okay, it's got to be less than 20. Now, look here, this is 273. This is 0. That's 0 degrees Celsius. So B and C have really got to be solids at room temperature. They can't be gases, okay? And A is a high melting point solid. Right, now you get a big drop in the melting point here. Where do you get that as you go across the, let's think also B, C, and D, because these are all kind of fairly low melting point things. These have got to be, they've got to be non-metals, haven't they? So we're talking about the non-metal side of the table. A is pretty high. Well, A is probably group 4, group 14, because you've got carbon, okay, which is a giant covalent, or silicon, which is also giant covalent. And then you get a big drop as you go from carbon to nitrogen or silicon to phosphorus. Right, now can you see that B can't be nitrogen, because you can see there it is a solid at room temperature. So B has got to be phosphorus. That is a solid at room temperature. And then the element C would be sulfur, and that's the one in group 16. So C is the answer here. That's it's C. And D would be chlorine, and you can see there that's D is it's got a melting point below 273, so it wouldn't be a solid. Chlorine, of course, is not a solid at room temperature. Okay, so C is the answer, and the element is sulfur. Okay, substance X reacts with water. A gas is given off, and the pH of the solution solution increases. Okay, so it's making it alkaline. Okay, the solution reacted with sulfuric acid, and you get a white precipitate. Well, that should start you thinking about barium, hopefully. You know, you've got some kind of barium compound going on in there. So it's got to be A or B, really, hasn't it? Now, if you put barium into water, do you get a gas? You do, because you will get barium hydroxide, and that will make it alkaline. That's going to make the pH go up, so that's good. And also you're going to get H2. Balance that. You will get a gas given off. So A is the answer. B is not right, because barium oxide, yeah, it will react with water to form barium hydroxide, but you don't get any, and that is alkaline, but you do not get any gas given off there. Okay, so A is our answer. Of course, if you add sulfuric acid to barium hydroxide, you will get a precipitate, because you're going to form barium sulfate. Whenever you get barium 2+ ions and sulfate ions in solution together, they will always precipitate out from a white precipitate. So A is our answer there. 15. So we've got magnesium nitrate and barium nitrate, and we're going to react them as shown. Right, so let's look at magnesium nitrate. If you add sodium carbonate solution, what will happen is you will get a precipitate of magnesium carbonate. So M is magnesium carbonate. If you add an excess HCl, that's going to react with magnesium carbonate to CO2, and you're going to get magnesium chloride in solution. And then if you add excess NaOH, well, you will get a precipitate of magnesium hydroxide. That's very insoluble. Okay, so let's just say which are precipitates. Yeah, that is a precipitate. That's a solid. This is aqueous solution. That is a solid. So you get, because he's asking us about how many are white precipitates. Okay, let's do the next one then. Q. Right, barium nitrate this time. Okay, so if you add sodium carbonate to that, you will get barium carbonate, which is insoluble. That's a precipitate. Then you add excess HCl, you're going to get barium chloride, and that is soluble. That is in soluble aqueous solution. Then you add excess NaOH. Well, barium hydroxide is soluble, so you don't get any precipitate there. You will get barium hydroxide, but it is not a precipitate. It's soluble. Okay, so how many precipitates there? We've got 1, 2, 3. So the answer is B. Okay. Nice. Okay, question 16. Oh, 15. I've missed question 16 off there. Sorry about that. Right, 17. Let's have a look at that then. Hopefully question 16 wasn't too difficult. Right, 17. The reaction of bromine with NaOH produces products with the same oxidation numbers in the same ratios as chlorine with hot NaOH. Well, we need to realize that what happens with if you react chlorine with hot NaOH, I won't bother balancing it, but remember, you get a disproportionation reaction. You get sodium chloride, so that's an oxidation number of -1 for the chlorine, and you get sodium chlorate 5. That's when you use hot, okay? If you use cold, you get sodium chlorate 1. Okay, so you get -1 and +5. So it says when you react bromine with it, you produce the same oxidation numbers. So let's do the reaction with bromine. I will balance that one. You're going to get Br2 plus NaOH goes to NaBr, NaBrO3, bromate 5, and you're going to get some water. Now to balance that, because so you've got a -1 oxidation state and a +5 oxidation state, you're going to need you're actually going to need they're going to react in a 5-to-1 ratio. So you're going to get 6 NaOHs. You're going to make 5 of NaBrs, and you're going to make 1 sodium bromate 5. So we need to balance that there. Okay. What mass of NaOH has been reacted? Okay. So we have got 30.2 grams of sodium bromate 5. Okay, that's NaBrO3. So let's work out how many moles of sodium bromate we've got. All right, moles. Is equal to mass over MR. We've got 30.2 grams of sodium bromate, and the MR of this thing, if you work it out, it is 150.9. Okay. So the number of moles there works out to be, that's exactly 0.2 more or less. Okay. Now look at the ratio. We've got a ratio here of 6 moles of that gives 1 mole of the bromate. So we're going to say the moles of sodium hydroxide then. It's going to be 0.2 times 6, which is equal to 1.2 moles. We need to work out the mass. Okay, so what's the mass of NaOH is equal to the moles times by the MR. So that's 1.2 multiplied by the MR of sodium hydroxide is 40, which gives us 48 grams. So D is the correct answer to that one. Okay, 18. Right, nitrogen dioxide reacts with unburnt hydrocarbon fragments, this is CH3, in the catalytic converter. Okay, which row gives the energy change for the reaction and a possible reason for it? Right, So energy, is it endothermic or exothermic? Well, it's going to be exothermic because you are producing there lots of carbon dioxide and water. So it's going to be exothermic. Now, why is that? Well, because carbon dioxide and water have pretty negative delta HF values. It's pretty exothermic when you make them. Okay. D is obviously a red herring. Breaking bonds actually would mean it takes in energy. It's endothermic. Okay. Right. Okay, so C is the answer to that one. In combustion, it's a combustion reaction, really, isn't it? Whenever you form CO2 and water, it's obviously burning things, combustion, very exothermic. 19. Which statement is correct? It's about ammonia. Ammonia reacts with alkalis to form ammonium ion. Well, it doesn't. Ammonia actually reacts with acids to form that, doesn't it? You need an H plus to form the ammonium ion. So that one is wrong. Ammonium chloride contains ionic covalent coordinate bonds. Right, now that is true because ammonium chloride is NH4 plus Cl minus. So it's got an ionic bond. And if you look at ammonia, well, ammonia is NH3, they're covalent bonds. But when it reacts with an acid, it forms a dated covalent bond to an hydrogen, so there's a dated bond there. So B is correct. Okay. So B is the correct statement. Just check the other ones. The bond angle in the ammonium ion is approximately 107. It's not, it's 109.5 because there's no lone pairs to distort the shape. The ammonium ion reacts with acids to produce ammonia. It doesn't, it's the other way around. It reacts with alkalis to produce ammonia. So B is the answer there. I just write down that NH4 plus will react with an alkali like OH minus to form NH3 and water. So B is the answer there. Right, the diagram shows two different compounds. All right. So the total number of structural isomers, including compound 2, that can be formed by sticking a methyl group onto the ring of compound 1. So how many could do that? Right. Where could we put it? We could put the methyl group there. Different color. It could go there. Right. Yeah, so that's 1. It could go there 2, 3, 4, 5. It couldn't go on this one here because that's all. It's forming a double bond and 2 singles. It's all not enough. You can't stick it on there. So that's 5 is the answer here. So it's got to be C or D. And the number of pi electrons. Okay. Well, how many pi electrons have we got in compound 2? Right. We've got 2 double bonds. 1 there and 1 there. Each double bond contains 2 pi electrons. It's 2 times 2 is equal to 4. So D is our answer there. There are 4 pi electrons. Each pi bond contains 2 electrons in it. So you've got a double bond. There's a sigma bond between 2 carbons. And the pi bond is like that. There's 2 lobes to the pi bond, isn't there? And there are 2 electrons spread out in that pi bond, 1 from this carbon and 1 from that carbon. So each pi bond has 2 electrons. And in compound 2, we've got 2 double bonds, 1 a carbonyl and 1 a carbon-carbon. Right, 21. Which compound has a molecular formula C6H10? Was a quick way of doing this. All right, so if it was completely saturated, C6, well, it would be CnH2n plus 2. Okay, so it would be H14. Now you can see there that it's H10. So that means each time you lose 2 electrons, so if it was CH, that would be 1 double bond. If it was 10, it would be 2 double bonds, or a cyclic, okay? A cyclic is like having 1 double bond. So we're looking for, or for each cyclic structure, you lose 2 electrons. Okay, so we're looking for something with 2 double bonds in it. So A would be the answer because look, it's got 1 double bond and it's got 1 cyclic structure in it. B would be wrong because there's only 1 double bond, so that would be C6H12. C, well, that's got 2 double bonds and the cyclic, so that would be like having 3 double bonds, so that'd be C6H8 for that one. And D is wrong because you've only got 1 double bond, so that would be C6H12. So A is the answer there. Okay, right. What is the structural formula of the major product when hydrogen bromide reacts with 2-methyl-butene? Okay. Right. So I've drawn 2-methyl-butene here in red. I've drawn that. Now, when hydrogen bromide reacts with it, we're going to stick an H on one carbon and a Br on the other one. Now, the major product, you are going to get the H sticking on there, because that means then you're going to get a tertiary carbocation as the intermediate, and you're going to get the Br sticking on that one. Okay, so which one of those is, and you're reading them on one line, so you've got to be careful. Well, it's not A, because look, the bromine is, it's not A. Is it B? Yes, it is. Look, we've got 2 CH3 groups there, CH3 twice, that one and that one. Then we've got CBr, then we've got CH2, then we've got CH3. So B is the correct answer there. '23. Which reaction is most likely to involve the formation of a positively charged intermediate? Okay. Now, these are all haloalkanes reacting with OH minus. Okay, so they're nucleophilic substitution reactions. And if you remember, if you get a tertiary, so if it's tertiary, what tends to happen is that the bromine can be lost, and you can form a carbocation there, okay, which is stabilized because you've got 3 alkyl groups around it. Now, that doesn't happen with primary haloalkanes. So primary haloalkane, you don't form a carbocation in that one. Remember, what happens is the OH minus has to attack first before you can lose the bromine. So you don't involve a carbocation. So we're looking for a tertiary. Right, 1-bromopentane is not tertiary, it's primary. So you've got like 5 carbons, haven't you? The bromine on the end, that's primary. Right, 1-bromo-2,2-dimethyl propane. Let's do B. Let's draw that out. Make yourself a bit of space. Okay, 1-bromo-2-methyl. Okay, so we've got 3 in a row. 2,2-dimethyl propane. So we've got C and C there, and we've got our bromine on there. Well, that is still a primary. Look, it is not a tertiary. The carbon to which the bromine is attached is only attached to 1 carbon, so that's not the answer. 1-bromo-3-methyl-butane. Let's try that. So we've got it in a different color. 1-bromo-3-methyl. Again, that is a primary haloalkane. That's not going to do it. So it's got to be D. Let's just check. What is it? It's 2-bromo-2-methyl-butane. Okay, so we're going to have a C there and a Br there. And that is a tertiary. Look, the carbon here, which I'll just put a red dot on, to which the bromine is attached to 3 of the carbons. So that is likely to form the carbocation. So our answer there is D. Right, here we have an infrared spectrum. Okay, right, so, okay, and it's got oxygen in it, C2H4O. Right, which bonds are responsible for peak X? Well, peak X is right in the middle of the carbon hydrogen carbon hydrogen, so it's got to be A or B. And so it's either got to be a CC double bond or a CO double bond. Well, that one looks very like a carbonyl. B is the answer there. Okay, rather than a carbon, which is in a similar region, but they tend to be a little bit shallower, like that sort of thing. So B is the answer. Okay, the structure of this subject, structure of conine. Okay, it can be synthesized by reacting with ammonia with a dibromo compound. Okay, so you're going to be getting a essentially you're going to get a nucleophilic substitution reaction there, aren't you? So just to show you, you had. So what happens is the lone pair that goes onto that carbon because it's delta positive, and the bromine breaks off. Okay, so now which compound? And this is going to we're going to replace, in this case we're going to replace 2 of the hydrogens on the bromine, aren't we? So it's got to have 2 bromine atoms. So what's it going to look like? Well, we're going to have, originally we should have had a bromine on there, and we should have had a bromine on there as well before that bit got added on. So let's just number those carbon atoms. So that's 1, 2, 3, 4, 5, 6, 7, 8. So it's octane. It is 1,5-dibromo octane. It's that there. 1,5-dibromo octane. So 25D is the answer. Okay. (26). Okay, structural isomerism and stereoism should both be considered answering this question. Okay, so 3-methyl-hexanol reacts with hot concentrated sulfuric acid. So what's going to happen there? We're going to get a dehydration reaction. So we're going to remove the OH, and we can remove a hydrogen. Then we can remove it from the carbon next door to that one there. Now the 3 carbons next door. There is that one there which are colored in red and green, sorry. That one which are done in yellow, and that one there which I'll do in purple. Okay, so depending on which hydrogen goes, you're going to get 3 different compounds there. So I'll just draw this. Let's say if the green one is where the hydrogen is lost from, I'll do that in green. Okay, so we'll end up with a double bond there. Okay, so that's one possibility. And let's look at that. You can see that this can exist as EZ isomers, okay? Because you could flip that one. You could have the 2 methyl groups they're on the same side, they come opposite side. So I'm going to do ×2 for that one because you've got EZ possibilities there, stereo isomers. Let's look at the structural isomer you get if you remove the hydrogen from the yellow one. Well, you're going to get, and you're going to get your double bond there. Now that doesn't have EZ isomers because you think this carbon here, draw as a dot, it's got 2 hydrogens, so it doesn't matter attached to the end, so it doesn't matter which way around it goes. So that's just one of those. And now let's do the purple. If we remove the one from the purple carbon atom, you're going to get this. We're going to get the double bond there. Now that can also exist as 2 EZ isomers because this big group here could be on the other side, couldn't it? Okay, so that's 2 times EZ for that. So that means we've got 3 structural isomers, and 2 of those can exist as 2 EZ. So we've got 2 plus 1 plus 2 makes 5 isomers. So our answer is C. (27). An organic compound T undergoes the following reactions. T is oxidized by hot potassium manganate 7. And okay, so it could be an alcohol. Yeah, it could be an alkene that's oxidized. Okay, we haven't got any alkenes there. We've got loads of alcohols. It could be so it's going to be an alcohol or an aldehyde. Okay, but look, which one of those react with hydrogen, with sodium to give hydrogen? It's only the alcohols, isn't it? All right. So it's got to be an alcohol. Okay, also, is it any old alcohol? Well, it is a primary or a secondary alcohol, isn't it? Because you can't oxidize a tertiary. So we are looking for something which is a primary or a secondary alcohol, right? A is a secondary alcohol, so that's the answer. B is an aldehyde, that's not right. C is an alcohol, but look, it's a tertiary alcohol. And D, well, that's got a ketone group in it, so that can't work. So A is the answer there. '27. An organic compound undergoes the following reactions. I've done that twice, so I get rid of that. Just done that one. 28. Okay. Compound X is treated with two reagents successively, forming compound Z. So you're going to oxidize it with a mild oxidizing agent, first of all, there. So I'd imagine probably you're going to turn that aldehyde group into a carboxylic acid. Okay, so we are looking at A or D, because well, in B and C, you've reduced it to an alcohol, so it's definitely not them. They are wrong. Now, then you react with NaBH4, or NaBH4 will reduce a ketone to a secondary alcohol, and you can see that that has happened here. And you haven't touched the NaBH4 will not reduce the carbon-carbon double bond, won't touch that because it's actually a nucleophilic reagent. Only electrophiles react with that. So D is wrong. So A is the right answer there. Okay, 29. Which reagent may be used to distinguish between propanone and ethanol? Right, 2,4-dinitrate written ethanol and propanone there. That is the answer because that will only react with propanone. That reacts with ketones, doesn't it? With carbonyls only. Bromine water won't react with either of them. Failings reagent won't react with either, and tolerance won't because they're tetraaldehyde. So A is the answer there. Okay, 30. Which compound is chiral? Okay, so that means we need 4 different groups attached to the same carbon atom. So let's just draw these out. So they're all butane, except for the last one. 1 chloro, 3 methyl. So we've got a chloro there and a methyl there. Now that's not chiral. There's no chiral carbon there because none of those have 4 different groups attached. This N carbon's got 2 methyls. Yeah. Let's try 2 chloro, 2 methyl. Now let's do that one. 2 chloro, 2 methyl. So let's change this a bit. Two chloro and a methyl there. That would be chiral. This carbon is chiral. 1 minute. Sorry, it's not chiral, is it? No, because it's got a methyl there, and it's also got a methyl there. That's not chiral, so that's not right. 2 chloro, 3 methyl. Let's try that. 2 chloro, 3 methyl. Now that is chiral because if you look at this carbon here, what have we got? We've got a CH3 attached. We've got a chlorine attached. We've got an H attached, and then we've got this propyl group here. Okay, so that is the answer. And just to check, 3-chloropentane isn't chiral because if we draw it out, so you've got 5, put a chlorine on there. Right, so that's not because you've got 2 ethyl groups, haven't you? 2, they're the same. So C is our answer there. Okay, these are these the last part of the paper where you have these 1, 2, and 3 bits. Okay. An atom of calcium can form a 2+ ion. Right. Now look in your periodic table. Calcium is atomic number 20. So if it's 48, how many protons, how many neutrons has it got? It has got 28 neutrons. It's got 48 minus 20. Has it got 20 protons? Yes, it has. Has it got 22 electrons? No, it would have not 20 electrons, it'd have 18, wouldn't it? It'd lose 2. So 1 and 2, so B is our answer for that one. (32) 4 elements X, W, X, Y, and Z have electronic configurations as shown. Okay. Which formula represents compounds that have boiling points lower than room temperature? Now, first of all, you can't be any of it. That means it's not ionic. Ionic compounds have high boiling points, don't they? So now you can see Y and Z are metals. They're going to form. They're only going to form. Y will form a 2+ ion. Z will form a 1+ ion. So you can't be anything with Y and Z in, with Y or Z. So it can't be that, and it can't be that. So it can only be 1. W and X are both, obviously, they're non-metals, so it's going to form a low boiling point covalent compound. It's actually carbon dioxide. If you look at it, it's got carbon and oxygen. So the answer there is 1 only, so it's D. (33) Which statements about enthalpy changes are correct? 1, the enthalpy change of atomization is always positive, always endothermic. Yes, it is. Okay. The enthalpy change when the CC bond is broken is positive. Yeah, to break any bond is always requires energy. That's true. The enthalpy change of a neutralization of a weak acid is always negative. Yeah, that's always exothermic. Yeah, so it's 1, 2, and 3. So it's A is our answer for that one. Right, 34. But catalyst, vanadium and pepsin both act as catalysts. Vanadium is a metal, pepsin is an enzyme. Which statements are correct for both? They will speed up any chemical reaction. No, they won't, because they're usually specific to any certain reactions. They can lower the activation energy for reaction. Yeah, that's how they both work as catalysts. And they are not used up. That's true. So 2 and 3 is right. So C is our answer there. Okay, which oxides, when placed in cold water for 1 day, will react with water? You've got magnesium oxide, aluminium oxide, and silicon dioxide. Okay, so this is about your period 3 oxides, right? That won't react with water at all. Aluminium oxide won't react with water at all. Magnesium oxide reacts very, very slowly to form magnesium hydroxide, which is very insoluble. So the reaction just occurs on the surface of the powder, really, but it will react very slowly. And so the answer is just 1, is D. A mixture of magnesium carbonate and magnesium nitrate is heated strongly in the glass test tube. Which gases are formed? Right, so magnesium carbonate, that will decompose pretty easily at a fairly low temperature to give you CO2. Magnesium nitrate, the magnesium nitrate, MgNO3, that gives you magnesium oxide, nitrogen dioxide gas, and oxygen gas. So you're going to get you're going to get all 3 of those gases there, all of them. So the answer is A. Right, so which statements about polyalkenes, so like polyethene, are correct? Right. They do not react with bromine in the dark. That is true, because they don't contain, in order to react with bromine in the dark, in the absence of UV light, you need a double bond. There's no double bonds in them. The double bonds have been broken when you form the polymer. Number 2, disposable by combustion products can produce harmful products. Polyalkenes, you only produce carbon dioxide and water, so that, as long as the temperature is high enough, so that's not true. And polyalkenes do not readily biodegrade. That is correct as well. It can produce anything, so we can't have that, because you can't have 1 and 3. So I suppose it can produce harmful products if you don't heat it at a high enough temperature. You can get so 1, 2, and 3. So A is the answer there. 38. Right. Compound, which could be compound Y, it reacts with alkaline aqueous iodine to form a yellow precipitate. Well, that's the iodoform test. Is what you need for an iodoform test. You need a methyl group, which is next to a ketone, or a methyl group, which is next to an alcohol. Okay, so either of those two. And the dichromate, this one here, changes the color of, so that means you can reduce the dichromate. So it's something you can oxidize. So that's testing for an alcohol, primary or secondary. And it can also oxidize an aldehyde. So it could be an aldehyde. Okay, so compound Y will do both of those. Well, ethanol will do both. Yeah, it's an alcohol, and it's got this CH3 group next to the alcohol. That's a positive iodoform test. 2, yeah, it's an aldehyde, so that will react with the dichromate, and you've also got the methyl group next to the carbonyl, so that will give you an iodoform test. 3 will give you a positive iodoform test, but you can't oxidize it, so it's not that. So it's 1 and 2 is B. Right, towards the end of the paper now. 39. Carboxylic acids can be made by several different reactions. Which statements are correct? The acid hydrolysis of that, no, it won't make ethanoic, it will make propanoic, won't it? Because you've got 3 carbons there, and this N1 will be turned into a COOH. So that's wrong. You can oxidize yeah, that's butanol. Yeah, that will oxidize it to butanoic acid. And this is propanal, and you will oxidize that to propanoic acid. So yeah, it's 2 and 3 there, so it's C. 40. Carboxylic acids react with alcohols to produce esters. Okay. Right, carboxylic acid X only forms one ester with a molecular formula C5H. Okay, let's see what it could be then. So let's try ethanoic acid. So we're going to have that bit, okay, from the acid, and it's the ester linkage. Now we've got 3 carbons to think about, so we could have CH2, CH3, that's one ester. But also what we could sort of rearrange this. So you could have this ester, where you've got CH3H. Okay, so you've got that. So ethanoic acid will give you 2 esters, so that's not right. Propanoic acid, let's try that. So propanoic acid, yeah, you're going to have CH3, CH2. And now you've only got 2 carbons to think about, and so you can only really have them like that. Okay, you can't have any branching there. So yeah, that will only give you 1 ester. And let's try butanoic acid. Well, butanoic acid, you've got, this is going to come from the butanoic acid. And you've only got 1 carbon to think about there. So it's only going to form that one. So those 2 and 3 are the answers. So the answer there is C. That is the end of the multiple choice paper.